Okay, so in this video we'll look at chapter 4, which is a Laplace transform backward analysis. So for this chapter, as usual, I will separate the chapter into several videos, and you will have to go through each video in order to understand them. Let's start with the first video, which is on the introduction. So this basically has a relation with the previous chapter. As you can see here, we still have the RLC circuit. So in our sinusoidal circuit analysis, in the previous circuit analysis, we have learned how to find the voltages and currents of a circuit, and that time the circuit we are having a constant frequency source, okay, constant frequency of voltages or currents. However, if we let the amplitude of the source remain constant, okay, but we changes the frequency, right? We changes the frequency of the source, then if we analyze the circuit, we can actually obtain what we call here is the frequency response. Okay, as you can see here, we have the circuit, right? And this is the input, and this is the output, right? And if we vary the frequency of the input signal, and then we measure the output signal, of course we'll get the frequency response of the circuit. Let's look at example of the frequency response. Okay, so if we vary the input signal frequency, right, you can see here the frequency changes, and then the response of the circuit is like this, which is the amplitude versus the frequency. Alright, then the phase versus frequency. This is basically the frequency response of a circuit. So the response depends on the combination of RLC in the circuit, right? So combination of R and C will give different response. Combination of R and L will give different response, and even different value of R and different value of C or L will give different response as well. So the frequency response of a circuit is unique, depends on the arrangement of the components RLC, and depends on the value of the components as well. Right, so basically the frequency response may be regarded as a complete description of the sinusoidal steady state behavior of circuit as a function of frequency, right? The response of the steady state behavior of a circuit as a function of frequency. So it depends on the frequency. You change the frequency, you change the response of the circuit in terms of the frequency. Alright, so let's go straight to the applications. Okay, what is the application of this frequency response? Why do we need to look at the frequency response of any circuit? Okay, so the frequency response has many important applications, right? This is especially in communications and control system. However, we also have the application in electrical system as well. Example here is in electric filters. This is very typical, okay, very common application of frequency response, that is to design electric filters, okay, to block out or eliminate signals with unwanted frequencies, and also to allow or pass signals of the desired frequency. So such as radio, TV, telephone system, okay, we use it to operate only one frequency, so that other frequency will not be blocked. All right, when we choose the radio signals, for example, we want this radio station at 100 megahertz, so we have to design an electric filter that will allow only 100 megahertz signals to be accepted, and to eliminate other frequencies. So in order to do that, we have to look at the frequency response of the electric filter or the electric circuit, right? So as you can see here, if we design this typical circuit of RC band pass filter, okay, we call it band pass filter, which is based on the combination of R and C. All right, so the frequency response of the circuit will look like this, okay. All right, so the signals or the frequency in this area, okay, will be blocked or will be eliminated, but the circuit only allow frequency signal in this area, okay. That is to pass or to allow at certain area of frequency, right, and to eliminate or to remove frequency outside this region. All right, so this is the frequency response that we need to look at in order to design this filter. So another application of frequency response in electrical system is what we call here is frequency response analysis, okay. So frequency response analysis is an electrical test that we perform on power transformer. This is a power transformer located at substation, electrical substation. So what the person doing is now performing FRE test, frequency response analysis test. So you can see here there are cables connected to the top of the transformers here, right? And the equipment will supply voltage at varying frequency, okay. You recall in the first slide that if you change the frequency, you can get the frequency response. So here this equipment will supply frequency 20 Hertz, 100 Hertz, and up to 2 megahertz. Alright, to obtain these two magnitude and phase plots. So these are the frequency response of the transformer, okay. So you can imagine that this is like a complex RLC network. So if we inject input voltage and measure the output voltage here, and then we will get the frequency response of the transformer. Right. So from the application is that based on the frequency response of the transformer, we can detect whether the structure of the winding or condition of the winding or the core laminated coin, the transformer is in good condition or damaged, like in the picture here. So if we compare the frequency response of normal and damaged transformer, it will give different results. So from that we know that there's a problem with the transformer. So this is an example of application where we use frequency response. So in the next video we will look at the transfer function.